All right. Again, ladies and gentlemen, if it feels like we're pushing, we are. I want to get this stuff into you. I want to give you time to take practice tests. I have 3 practice tests written for you that are similar to what you're going to see on the final exam. We are going to try to give you a day to do it, go over it, give you a day to do the next one, go over it, give you a day to do the last one, and then go over it. So, because it does us no good if we don't go over them. Okay? And it does us no good if you don't take the time to try to do these. The idea is we're going to try to get you familiar with the clues that I'm giving you, how they're worded and things like that, and hopefully you'll become more comfortable with them. Please remember, again, you guys are pretty good about most of the things in class as far as the missing work and stuff like that. Most of you are not. Okay? Here's the one thing that I will tell you, ladies and gentlemen. Okay? If you are missing something, get it in. Give yourself as much cushion as you possibly can going into the final exam. You do not want to go into the final exam with a score of a 60.00 and have to pass the final exam to pass the class. You'd like to give yourself some cushion. Now again, some of you go into Infinite Campus. Look at your grade. Some of you are missing a quiz. Some of you are missing a lab. You've got until Thursday to get them made up. After that, it's going to stay, and now you're relying on the final exam. Okay? Not a good plan for you to do that. Okay? So I got no question of the day for you today. Your final exam is next week, Thursday, 7:30 till 9 o'clock. Okay? Again, we'll go over what's going to be on it. It's an open note, open quiz test. Okay? Today we're going to start getting into talking about some molecular geometries after we finish up some of the things that we were doing yesterday. Okay? So where I want to begin, ladies and gentlemen, is let's take these back out again. Okay? Let's take these back out. Now, again, we're writing some things on here, things that are trends in families, things that are trends in in certain spots of the periodic table, things like that, ladies and gentlemen. Okay? So before we do, which of the following is not a property of a metal, ladies and gentlemen? Which one? Brittle. Being brittle is a property of a? Very good. Which metal is the more reactive metal of these 4? Farhan. What? Strontium. Why? No. Cesium. Because it is the closest to francium. Strontium is higher up and 1 over. Okay? You want to be as far to the left as you can, and you want to be as far down. That is cesium. Okay? Which nonmetal is more reactive? Oxygen. You want to be as high up and as far to the right or as close to fluorine as you can be. Oxygen is the one that is right next to it to the right. Now, so tellurium is in that same family as oxygen, but because it's further down, it's not going to be as reactive. Nitrogen and arsenic are further to the left than oxygen is. They are not going to be as reactive. Which element has the largest ionic radius? Which one has the largest ionic radius? Now, just so that we are clear here, ladies and gentlemen, let's look at our 4 choices. Okay? So our 4 choices, ladies and gentlemen, are calcium, argon, bromine, and gallium. So, let me do this for us, ladies and gentlemen. Maybe not. I thought this would be easy. calcium. Right there. Argon. Right there. No, you're not. I'm not showing it to you yet. Gallium and bromine. All right. So now I marked the 4 of them here, ladies and gentlemen. Here is calcium. Here is argon. Here is gallium. Here is bromine. Of those 4, which one would have the largest ionic radius? Argon? I'm asking.
Yeah, or would it be bromine since calcium is going up there at that side and then it hits bromine, so then it increases.
Okay, so let's talk about this real quick because this is a tough one. Okay, ionic radius as you go down increases. Okay, so we're looking for something further down. That means bromine is further down, and that means calcium is the furthest down. Okay, all right, but we also said that as you go across the period, ionic radius drops until you switch from metals to nonmetals. Then it has a big jump. Then it starts going down again. Okay? So, argon and calcium. Well, first of all, magnesium. Well, no, sorry. Argon, calcium, bromine, and what's the last one? Gallium. Here. Okay. So, bromine is the furthest down of all of these. Okay? But calcium and gallium are in that same row. But they are metals. Metals in the same row of nonmetals will always have a smaller ionic radius. Always. So therefore, because bromine is in the same row as gallium and as calcium, bromine will have a larger ionic radius. Okay? Bromine will have the larger ionic radius. And it has to do with the fact that bromine has 4 energy levels around it. Because remember, this is ionic radius. Bromine is going to look just like krypton. But gallium and calcium are going to look like what noble gas? They're going to look like argon. So which one is bigger, argon or krypton? So therefore, that's why bromine is the largest. Okay? Questions on that? We're good? Okay. All right. That ain't right. Calcium is not right. It should have been bromine. Sorry, I got to correct that. Which of the following elements has the largest ionization energy? Which of these 4 elements? Sodium, chlorine, aluminum, or argon? Sodium, here. Chlorine, here. Aluminum, here. Argon, here. Now, they're all in the same what? They're all in the same period. So this is not a trend where we're comparing things that are in different periods. So what is our trend for ionization energy as you go across the periodic table? It does what? It increases. Okay, so which one is the furthest to the right? Argon. Argon has the highest ionization energy. Good. Questions? All right. So those were our practice questions for today, ladies and gentlemen. All right. Now what I want to do is let's go and let's look at some things that we were talking about yesterday when class kind of ended. Now, all right. So again, ladies and gentlemen, we were putting a bunch of information onto our periodic table. Okay. So here's our periodic table, ladies and gentlemen. We were putting a bunch of information on it, and that's good. That's what we want. We want you to be able to find things easily. We want them to be right there for you. So so that you can look them up. Okay? Please remember these 4 spots right here, even though they're next to each other, technically on this periodic table, they differ in atomic number by 11. That is a great clue to use, ladies and gentlemen. And I will tell you, I use things like the element named after the high point and the low point of a wave are next to each other on the periodic table, but they differ in atomic number by 25. So that means crest and trough go somewhere in these 4 squares. Now, if you have an element in one of these 4, it can't go in that same row because they need to be right next to each other. But then the last part of the clue has to be some way of me telling you which one is first and which one is second. And that's where I may tell you that even though they're next to each other, the element named after the high point of a wave has a higher ionization energy. Well, what happens to ionization energy as you go across? So therefore, the one with the higher ionization energy would be second. The one with the lower ionization energy would be first. That is a lot of information to process, but it is all things that you should be able to handle by the time that we are done. Questions? All right. So, I believe yesterday I left off where I was talking about the noble gases. We said they were inert. Another word for a noble gas is inert. They're monatomic, meaning they exist as a single element, and they are unreactive. All of those things describe the noble gases. Now, where would be the man-made noble gas? Man-made noble gas. No. No. Where is the man-made noble gas? Group 18, period 7, down at the bottom. Why? The man-made ones go from group 13. You are correct, Abby. All the way across the bottom. But group 13, that's not a noble gas. So the man-made noble gas is right there, group 18, period 7. Where is the man-made halogen? Group 17, period 7. Okay? So the man-made ones are down at the bottom here. Keep that in mind. That is a great clue as well. Okay? Because it gets you into that area. But then I have to do something a little more specific. Where's the man-made element with 3 valence electrons? Group 13, period 7. Very good. Questions? Okay. Where is the smallest ionic radius? No, let me rephrase that. Sure. Smallest ionic radius with 5 valence electrons. Group 15, good. Where's the smallest ionic radius in a group? Would be at the very top. It would be at the very top. Now you're putting a couple of ideas together, right? Ionic radius increases as we go down. So where's the smallest? Near the top. Why group 15? Because that's a group with 5 valence electrons. Very good. Questions? Okay. All right. So this is where I left off the other day, and I did the radioactivity part of this. We talked about elements that are 82 or higher are all radioactive, and we marked that at the bottom of our periodic table here for you. We marked that down here, radioactive here, radioactive across the bottom, right? Okay, well, let's quickly explain what it means to be radioactive. What it means to be radioactive, ladies and gentlemen, is that the nucleus of the atom is literally going to break apart. It is not a chemical reaction. It is a nuclear one. And nuclear reactions Literally, the nucleus of the atom breaks apart and it does one of three things. Okay? Thing number one is it can give off what is called an alpha particle. What an alpha particle really is, ladies and gentlemen, is it is a helium atom. Okay? Now, a helium atom has 2 protons in its nucleus. It also has 2 neutrons in its nucleus. So when an atom undergoes alpha decay, it loses 2 of its protons from its nucleus. So let's say the original atom had 84 protons. If you lose 2, how many are you down to? If you had 84 and you lose 2 protons, how many are you down to? 82. But more importantly, ladies and gentlemen, you have literally changed from being polonium to being lead. Okay? So we are going to want to write this somewhere, ladies and gentlemen. Now, I don't care which periodic table you choose. I am going to use this one only because it has the radioactivity on it. And I am going to make a note that says alpha particle. Means minus 2 protons per particle. You can lose more than 1 alpha particle at a time. You might lose 2. I'll blow that up because I see Karina going, God, can he write any smaller?
Can you?
I can. Trust me. You want to see?
No.
Alpha particle, minus 2 protons per particle. That's what it means. So what that means, ladies and gentlemen, is you're going to back up 2 spots on the periodic table. Wherever I give you, you are going to back up 2 spots. So if we talk about this element right here, losing an alpha particle, 1, 2, you go back 2. Okay? If we talk about this atom right here, losing 2 alpha particles, how far do you got to go back? 1, 2, 3, 4. Okay? Now, please understand, your clue, each particle loses 2 protons. Okay? Loses 2 protons. So, again, this is another one where, okay, the element with the longest wavelength of visible light. What element on your blue sheet has the longest wavelength of visible light? Which element on your periodic table has the longest wavelength of visible light?
Oh.
Don't tell me you know and not tell me the answer. Anybody?
Wait, you saw the periodic table?
What element on your list has the longest wavelength of visible light? What happens to wavelength as we go across the spectrum, ladies and gentlemen? Okay, so what colors are you looking for that would have the longest wavelength? Red first, orange, then yellow. Is red on your list? Red is on the list, right? So that would be the element with the longest wavelength of light. Okay? That element is created when branium undergoes alpha decay. Okay? So I'm going to tell you where branium is. Branium is right here. So where would red go?
Red.
If it is created when branium undergoes alpha decay, it would go 2 to the right to Bi. Okay, it would go 2 to the right to Bi. Right.
Is it because of the...
To the left, right? To the right?
Back to the left, back.
You said because of the
Yeah.
Did I? I'm sorry. I'm sorry. Okay. Now remember, radium could undergo alpha decay as well. And if it lost one alpha particle, what would it become? It would become radon. Okay? You're going to go back 2 for every alpha particle. Question.
So basically, going 2 to the left.
2 to the left minus 2 protons. Okay? All right. So, beta particle is different. In a beta particle, what happens is a neutron in the nucleus of the atom breaks apart into a proton and an electron. Well, what doesn't belong in the nucleus, protons or electrons? So that electron gets shot out of the nucleus. But what happens is what gets left behind is instead of being a neutron, you now have a what in your nucleus? One more proton. So beta particle plus 1 proton per particle. This means that it is going to move 1 to the right. Correct. This means that it is going to move 1 to the right. Okay? So, alpha decay, you are going to move back 2 places to the left. As we said, I don't know my right from my left. Beta decay, you are going to move 1 forward or 1 to the right per particle. Questions? Okay. There is a third type of decay, gamma. But here's the good news. For gamma decay, ladies and gentlemen, gamma decay, nothing changes. Where's my cursor? Gamma decay, nothing changes. No protons, no nothing. Okay? Alpha, 2 back per particle. Beta, 1 forward per particle. Questions? Okay. 1930 periodic table on the wall over here, ladies and gentlemen. 1930, they had yet to discover and name all of the elements. Here's element 85. There is no symbol for it. They hadn't named it yet. Here is element number 87. Again, they had not named it yet. Do you remember when we talked about how Mendeleev said that there were elements that had not yet been discovered, and here's where they belonged on the periodic table? Okay? Well, one of them, ladies and gentlemen, was the element gallium. Gallium was an element that had yet to be discovered. So when Mendeleev said, here's the spot where gallium goes, it goes under aluminum. They used a term for that, ladies and gentlemen. They used the prefix eka. Eka means 1 below. Okay? So in other words, if we want to describe that spot of gallium right here, originally they called it eka aluminum, meaning 1 below aluminum. Okay? So that is what the prefix eka means. I would write that on the bottom of your periodic table as well. Eka means 1 below. Eka something means 1 below. What? So in other words, I may tell you that the element lithium, before it was discovered, was called eka-Easteion. Well, Easteion is one of your clues, right? That clue has to be on the periodic table somewhere. So if this is the spot where you had Eastion, where would you put lithium? Right below it. That's what that means. Right below it. That's what that means. Good. Questions? All right. So that takes care of all of this stuff. Any questions? Okay. So, here we go, ladies and gentlemen. Come on. All right. Ionization energy we already talked about. We have already discussed this. But here's the kicker to ionization energy. Ionization energies, there can be more than one of them. What? Well, there could be up to 7 in reality. I stopped after 4 because I'm going to show you a pattern. Hopefully you're going to understand the pattern, and then you could expand that pattern if you needed to. Okay? So here's the pattern, ladies and gentlemen. We are going to talk about what family, grab this one, has the highest first ionization energy. What family on the periodic table has the highest first ionization energy? Takes the most energy to get it to give up 1 electron. What family? Group 18. So, I am going to, ladies and gentlemen, in group 18 here, I will zoom out in a minute because now I'm going to write bigger to keep Karina happy. Okay? I'm going to do it anyway, Karina, even if it doesn't make you happy. Okay? So over here, group 18, highest first ionization energy. IE to me is ionization energy. If you can't remember that, you're going to have to write that down. In other words, to remove the first electron, this family takes the most energy. Okay? This family takes the most energy. What family has the easiest time giving up 1 electron? The first one, the alkali metals. They have the lowest first ionization energy. That's the first. Okay? Technically, if you wanted to get more specific, top of the family, harder to remove an electron. Bottom of the family, easier. But again, we're just talking about families here, okay? Fair enough? Now, what if you want to remove a second electron? What family has the highest second ionization energy? Which one? No, not the halogens. That is a good guess, though. You went back one, right? Nope, it's not the halogens. Second group, group 2? No. No, not the which ones, Abby? I'm sorry. Was it alkali or alkaline that you said? Nope. The alkali. These have the highest second ionization energy. Here's why. Please think about this. This family wants to lose how many electrons? This family wants to lose how many electrons? 1. And when it does, it becomes stable. So when you come around saying, can I have an electron? It's like, yeah, definitely take one, right? Doesn't need a lot of energy to get it to give up one. Okay? But when it loses one, what does it look like now? It looks like a noble gas, right? Literally, it has the same configuration as a noble gas does. So why do you have a hard time getting a second electron? Because they look like noble gases after losing one, correct? Okay, so they don't want to give up a second electron. What family does want to give up a second electron? Which family would like to lose two? Alkaline earth metals. Very good, Karina. So this family here has the lowest second ionization energy. Okay? Because that's the energy needed to remove the second electron. So, the highest is group 1, the lowest is group 2. So what if you want to remove a third electron? Give me either the highest or the lowest, either one, I don't care.
So if the alkaline earth lost two, then they become stable?
Yep.
Okay.
So which one has the hardest time giving up a third electron?
Then it would be the second one because they're only stable now.
When you say the second one, what do you mean by?
Alkaline earth.
Very good. So while this has the lowest second ionization energy, it has the highest third ionization energy. Where's the lowest third ionization energy? Are you seeing the pattern now? So remember, group 13, they want to lose 3 electrons, right? So you ask them to give up a third electron and say, yeah, sure, take it. I don't care. I don't want it. But family, the boron family, group 13, what is it going to have the highest? The highest fourth ionization energy. Where's the lowest fourth? So do you see the pattern? Do we need to continue? Okay. Questions? Now, I'm going to show you an example. My suggestion would be for you to write this down, but let me show it to you and explain it to you first. These are consecutive ionization energies. Here they are. 125 kilojoules, 240 kilojoules, 480 kilojoules, 605 kilojoules, 732 kilojoules. Now, I need you to look at those numbers and tell me which one is out of place. Farhan. Why? Run that by me again, this time in a little louder English.
It was going by 100 until they jumped by 2. 220.
Okay. So the first one, about 125. The second one, about 115 more, right? Then all of a sudden 240, right? Then back down to about 125, then back down to 127, correct? This is the unusual one, right? Which electron was that you were removing? If these are consecutive, this is the first electron, this is the second, this is the third. So this has the highest which ionization energy? Third. What family has the highest third ionization energy? So this element has to be in the alkaline earth metals. Has to be in the alkaline earth metals. So again, it's not that these numbers are exactly the same, 125, 115, but they're close, right? Here to here, 125. Here to here, 127. They're close. But here to here, 240. A much higher number. That's what you're looking for. That tells you which electron had the hardest time being removed. Questions? So if you want to write these numbers down and circle this one and say it's the highest third ionization energy, that's your choice to put that example down somewhere for yourself. Your choice. Okay. So again, we went through these, right? We're good? Any questions on ionization energies? Yes, no, maybe so. Okay. These, ladies and gentlemen, are what are called Lewis structures. And that is what we are going to get into next. Okay? Lewis structures are looking at the valence electrons on an atom. The valence, which are where? Where are valence electrons? The outermost ones. That's the only ones I care about, the outermost ones. Everything in group one, the alkali earth metals, has one valence electron, meaning this is what they will look like. I don't care if it's lithium, sodium, potassium, rubidium, cesium, or francium. They will have one dot over it because there is only one valence electron. Questions? Beryllium will have two dots above it because they have two valence electrons. Why are the two dots above it? What part? Go back to electron configuration. What fills up first in each energy level? Okay, so this would be S1. This is S2. Good. But beryllium, magnesium, calcium, strontium, barium, radium, all would look exactly that same way. Questions? Now you get to boron. Boron has three valence electrons. The S2, what would this be? A P1. A P1. So boron, all the way down, aluminum, gallium, indium, thallium, niobium. Questions? What happened here?
It's spread out.
Yeah, we had a term for that. Who could tell me what the term for this was? When that electron moved from the S to where? To a P. There was a term for that. What was the term for that? We use it to explain things like copper's multiple charges, iron's multiple charges. Started with a D. No. Something orbital. This, ladies and gentlemen, is a degenerate orbital. Instead of two dots at the top, and one here and one here, these spread out. Now here's the importance of that, ladies and gentlemen. That means that this atom right here could share how many different electrons? Four. Could share 4 electrons with another atom. Okay? This atom has 5 valence electrons, correct? How many electrons could it share? Only these 3. It can't share these. Why? Because they're already full. They're already paired up. So you cannot share it if they're filled up. You can only share the ones where you have 1 electron there. Make sense? How many can oxygen share? 2. How many can fluorine share? 1. How many can neon share? None. It's stable. Okay? Go back to boron. How many could it share? 1, the way it is right now. But if carbon can go through a degenerate orbital, could boron? So 3. But if you only have 3 to share, ladies and gentlemen, you will never become what? Because if you only have 3 to share, how many electrons? Now remember, to share, that means you're going to donate an electron and some other atom's going to donate an electron. You're going to share those, right? So if another atom comes along and shares with carbon, how many atoms could share with carbon? 4. And if I get 4 that do that, I can fill up around the carbon, right? Okay. But boron only has how many to share? Will it ever become stable? No, because it needs 8 electrons around it to be stable. So boron can do this. Boron can share electrons, but it cannot become stable. Can carbon become stable? Can nitrogen become stable? By making how many bonds? 3. Can oxygen become stable? How many bonds? 2. Can fluorine become stable? How many bonds? Only 1 though. Only 1. By the way, there is another element that can do the same thing as fluorine, but is not in that family. What other element only needs 1 more electron to fill it? What? Nope. Remember, fluorine is a metal or non-metal? What other non-metal only needs 1 electron to fill it up? Francium's not a non-metal. It can't be anything in here, right? These need how many? Can't be anything here. These need 3, 4. No, well, all of group 17, you're correct. I agree with that. But they would be that way. But what other element besides group 17? Well, one other element besides group 17 needs one electron to fill it. And it's an exception. What? Hydrogen. Hydrogen is the same way as the halogens. It has one electron, but it only needs two. These have 7 and only need 8, which is why they can only share one electron. Hydrogen can do the same thing as a halogen. Okay? Hydrogen can do the exact same thing because it has one electron, but it only needs 2 to fill up. These have 7, they only need 1 to fill up. Okay? Questions? All right. So you ready, ladies and gentlemen? You ready? Let's talk about VSEPR. VSEPR means, ladies and gentlemen, means my slide's not working. Thank you. VSEPR is valence shell electron pair repulsion. Valence shell electron pair repulsion. I am not going to test you on that. Not going to test you on that, but that's what it means. What it does is it determines the shape of molecules in covalent compounds. It determines the shape of molecules in covalent compounds. So, covalent compounds, ladies and gentlemen, where atoms are doing what with electrons? Atoms are doing what in a covalent compound with their electrons? They are sharing them. They are sharing them. Okay? So, it is a model to explain the geometry, how something looks, based on minimizing the repulsion of shared electrons and unshared pairs of electrons. Let me show you what I mean by this. When atoms form covalent compounds, they do so by sharing unpaired electrons. That's what we were just talking about. Carbon has four unpaired electrons. Nitrogen only has how many? Nitrogen only has how many unpaired electrons? 3. Oxygen has how many? Fluorine has how many? Chlorine has how many? Bromine has how many? Hydrogen has how many? 1. All of those only have 1. Okay? All right. Each covalent bond is a pair of shared electrons between two atoms. This atom and this atom say, okay, I can't give you electrons because I don't want to lose any. We're going to share them between us. We are going to share them between us. The total pairs of electrons is that which is around the central atom. The central atom. Okay? Bonding pairs is the number of shared pairs of electrons between the two atoms. So how many electrons are they sharing between the two? What is the maximum number of pairs that you can share? 4. But nitrogen cannot share 4 pairs, can it? It can only share 3. Oxygen can only share 2. Boron can only share. How many can boron share? Not 5. Doesn't have 5. It has 3. Boron can only share 3 as well. The difference is boron will not be stable. Nitrogen will. I'll show you that. Lone pairs are pairs of electrons around the central atom that are not involved with bonding. So that's those 2 electrons on the top of nitrogen. That is the 2 that are on the top and 2 that are on the bottom of oxygen. They're a pair, but they cannot share because they are already paired up. The bonding in lone pairs determines the geometry and the angle. Here's the good news, ladies and gentlemen. This is all basically a trend on the periodic table. So let's begin. Okay? By the way, you get something called hybridization. What's a hybrid car? What two?
I don't know.
What's a hybrid car? Come on.
Who knows about cars?
What is a hybrid car? What does that mean? That it runs on what?
Gas
Gas
and
and
Electricity.
electric.
Yeah.
Gas and a battery. So is it a gas car?
Yeah.
Kind of. Is it an electric car?
Yeah.
Yeah. It's a mixture of the two, correct?
Yeah.
Okay. Well, you remember how we have S's and P's in the outer energy level. Those are the orbitals. Well, when they share with another atom, it's a hybrid. It's no longer an S or a P. It is some mixture between the two. So we are going to talk about that. Okay? That's what hybrid means. A combination of the two. Okay? So, there are no longer S's and P's and D's and F's. Okay? There is a hybrid of S's and P's. D's and F's don't get involved in this. At least not that we're going to worry about here. All of these compounds are between a member of the representative family. In other words, carbon for the carbon family, nitrogen or phosphorus for the nitrogen family, oxygen, sulfur, or selenium for the oxygen family. That's the representative family. Those will be the central atom because multiple atoms will be connected to them. And either a halogen, like fluorine, chlorine, bromine, iodine, or hydrogen. Why? Because all of those halogens and hydrogen all only need how many more electrons to fill? One. Fluorine, chlorine, bromine, iodine all have 7 electrons around their nucleus. They only need one more. Hydrogen has 1 electron. It still only needs one more because it only needs 2 in the first level. Okay? So wherever we put hydrogen, we could substitute a halogen. And wherever we put a halogen, we could substitute hydrogen. Be the same thing. Okay? All right. So here's the whole thing, ladies and gentlemen. Here's the whole shebang. Even going into elements that probably shouldn't do this, like the alkaline earth metals. Okay? Now, let me explain what we have here, and we start down here. Okay? Beryllium has how many electrons around it? How many electrons around beryllium? Try again. Try again. 2. Here's beryllium. It only has 2 electrons around it. Now, I have cheated down here, ladies and gentlemen. I cheated. Be would have 2 electrons around it. Okay, that's all it has. So now if we bring a fluorine in, fluorine would have how many electrons around it? Nope. Try again. Fluorine.
Oh, 7.
Now, what does that mean for that fluorine now?
Balance.
It's stable. It's stable. Balance. Let's stay with stable because that's the term we were using before, right?
Yeah.
Okay. That makes that fluorine stable. If another one comes in here, it will do the same exact thing. So I'm sorry, I don't have all my dots around fluorines here and here like I should. Okay? But understand it would be filled. Now the beryllium in the middle here, is it stable? Why? Well, it's not losing them. Technically, in this model, it's sharing them, which beryllium probably doesn't want to do. But here's the real world. we talk about there being an ionic bond and we talk about there being a covalent bond, right? Ionic bond atoms lose electrons or gain electrons. Covalent, they share. In the real world, ladies and gentlemen, it's probably a little bit of both. It's probably a little bit of ionic and covalent, so we're kind of overlapping here. But we're explaining this just to show you a pattern, okay? So this central atom in the center has how many pairs of electrons around it? How many pairs around the beryllium just in the center? 2. That's the total pairs here, 2. Okay? Now, are they both bonding pairs or are they lone pairs? Bonding pairs are pairs that are in between 2 different atoms. Lone pairs are pairs that are there but have no other atom to them. So are these bonding or lone pairs? They're both bonding. They are both bonding. Now, I do want to show you one other thing before I get too far here. We could do this exact same model with hydrogen. The only difference, hydrogen only needs how many electrons to fill it? Total. Total of 2, 1 more. You're absolutely correct, Evan. 1 more or a total of 2, right? So is this hydrogen stable? Yes. Would this hydrogen be stable? So either way, the fluorines or the hydrogens are stable, but not the central atom. Okay? But this and this react the same way in this compound. They share 1 pair. They both become stable. Fair enough? Okay. So, if there are 2 total pairs, if they are both bonding pairs, and if there are no lone pairs, here would be the shape of this molecule. Just like this. This represents beryllium. This represents the fluorines, chlorines, bromines, any halogen, or it could represent hydrogen. Here, the white sears are representing hydrogens. Here, the green sears are representing a halogen. Same exact shape, doesn't matter. I could take this off, I could put this one on, and it does not change a thing about the shape of this. Okay? But the reason for the shape of this is because this is the way that these 2 atoms get as far away from each other as they possibly can. That's that valence shell electron pair repulsion. This shape gets them as far away from each other as they can possibly be. Questions? What is the shape here? A line. Linear. What is the angle between this, and this? Straight line, 180. That is the shape that gives this geometry the furthest away for the electrons on the other atoms. Now, remember, beryllium has 2 electrons, right? This one is in the S, correct? Where would this one be? In a P. So the hybridization is called sp hybridization because it involves an S and a P, but they're not really S's and P's anymore. There's some combination of them. Just like the car is not electric and not gas, some combination of that. Fair enough? So this is the way we would explain any member of the alkaline earth metals. Okay? If we had to, this is the way we could explain it. Now we go over one to the boron family. The boron family will do this, ladies and gentlemen. The boron family will take its 3 electrons and share them with other nonmetals. Now that doesn't make it stable. Why? Because if you look at boron here, how many electrons are around it? How many? 2 here, 2 here, and 2 here. When it's sharing, it gets up to 6 electrons, but that's still not how many? 8. So there are 3 pairs that it can share, here, here, and here. 3 of them are all bonding pairs, no lone pairs. The shape of this would be what we call trigonal planar. Trigonal like a triangle, right? But planar meaning it is what? Flat. A flat triangle. Why? So that this, and this can get as far away from each other as possible. This is the shape that gets these 3 atoms as far away from each other as possible. Now, for the hybridization, I have to be using an S and how many of the P's? 2. So therefore, the hybridization is sp2. Here, I was using 1 S and 1 P. That was sp hybridization. Here, I'm using 1 S and 2 P's. That's sp2 hybridization. Okay, now we go to carbon. Carbon can form how many bonds? Try again. Carbon can form how many bonds? 4. It can have 4 electrons, 1 in the S and 1 in each of the 3 P's, correct? 4 electrons. This is the shape that you get. Now, if you look at carbon up there with fluorines, what shape is that? Down at the bottom, what shape is the Lewis dot diagram, would you say? What does that look like? A T, a cross, something like that. How does this look like a T or a cross? Well, if you hold it like this. This is 3 dimensions. That's 2. You can't see that those fluorines on the top and bottom are going away from you and the ones on the side are coming out at you. That is the difference between a 2-dimensional model and a 3. Here's this. That's a good model. It's just on paper you can't show things coming out or going away, right? Here you can. By the way, this is what is called a tetrahedral. What does tetra mean? 4. So this shape means that this triangle right here is the exact same as this one right here, which is the exact same as this one right here. And it's also the exact same as the one on the bottom. Tetra, 4, hedral, shapes that are exactly the same. So if you were to look at it, ladies and gentlemen, this kind of looks like a pyramid. A pyramid where all 4 sides, including the bottom, are the same. Okay? Are the same. All right. So now, ladies and gentlemen, let's go one more. Let's go to the nitrogen family. We're going to skip that non-degenerate orbital. We're going to skip that for now. The nitrogen family, ladies and gentlemen. Now nitrogen has a pair of electrons on top and then 3 lone electrons, right? Well, here is the lone pair of electrons. Here are the 3 shared pairs. Okay? So nitrogen can only bond with 3 other halogens or 3 other hydrogens. It doesn't have any way to do anything with this pair other than leave it. But if you look, 2, 4, 6, 8 electrons, this nitrogen is now what? It has 8 electrons. It is stable. Now, again, there are 4 total pairs of electrons around nitrogen here. 1, 2, 3, 4, right? But they are not all bonding pairs now. How many are bonding?
3.
Only 3 of them. And there is what is called a lone pair. And that gives us what we call a trigonal pyramidal shape. these electrons here push these atoms away. Why? Because this is a lot of negative charge here. That's 2 electrons there. Unlike here, where it could be planar because you didn't have those electrons here, this pushes these away a little bit. So this, ladies and gentlemen, is still like a what shape? Like a triangle or a pyramid, right? But the difference is this and this one are not the same. Trigonal pyramidal means that only 3 sides are the same, not all 4 like here. And it's because of these lone pairs of electrons here. Okay? So now we get to oxygen. Oxygen, ladies and gentlemen, has 2 lone pairs of electrons. 2 of them here. But it also has 2 electrons that it can share. Okay? So it shares them. It shares them with hydrogen. 2, 4, 6, 8 electrons around the oxygen, right? That makes it stable. Hydrogen, 2 electrons around it. Stable? Yes, hydrogen only needs 2. This hydrogen only needs 2. You don't like it? Put a fluorine in here. Fluorine would do the exact same thing. And it would be stable. 4 total pairs. Now only 2 are bonding though. Here and here. 2 lone pairs. So we get a different geometry. We get what is called bent. We're talking about here, here, here. This is the geometry we're looking at. These lone pairs of electrons push these away from each other. It's no longer linear. It's no longer a straight line. These areas of negative charge push these away. A bent geometry. That's it. Okay? By the way, this sp3 hybridization, because we're using the S and all 3 P's. This sp3 hybridization. Doesn't matter if they're lone pairs or not. There's still an area being used. This sp3 hybridization. This sp2. We're only using 3 total pairs. Okay, just enough time. This is a halogen in the center with a hydrogen. Now, 3 lone pairs here, right? 1 bonding pair, still sp3 hybridization. All 4 orbitals are being used. But these are just lone electrons, so what's the geometry between here and here? What? Nope. That's not 90, that's 180. That's a straight line. We're back to linear again. These are pushing away, but since there's only 2 points, 2 points has to be a straight line. Linear geometry. Okay, ladies and gentlemen, tomorrow we'll put this on your periodic tables for you. Okay? Good work today, ladies and gentlemen. Very good work today. Assuming you understood anything I said, I mean, that was very good work for you. Well, believe me, Farhan, we're going to find out if you understood it or not.
Yeah.